Okay, so we'll start the next chapter. The first part of the next chapter is actually mainly refreshing your memory about what we studied in Math 3C. We are supposed to use the notion of derivative to locate the extreme points of a function. By extreme points, I mean maximum points and minimum points. And we also had a different type of points. Do you remember what was the name? Yes?
Inflection point.
Yeah, inflection point came later, but before that, yes? A Terrace point. Yeah, so we had 3 points to understand them. So let me just try to review a little bit. So if I have a function, for example, like this, okay. I want today's lesson, we want to understand the behavior of a function, not using its graph, but using its formula, okay? But to understand what is going on, I turn the logic upside down. I am assuming that the graph is given to you, okay? And then I want to understand how can I find these important points on my graph, yes? There are some names for them. So this point is a local maximum point. Why is that? Because this point is higher than the points in the neighborhood of that point, yes? Of course, this point is not as high as this point, for example. This point is lower than that point. This is why we say that this point is locally a maximum. Yeah, so it means that the height of this point with respect to the points close to it is higher. That is the meaning of being a local maximum. Yes? And the same is true, for example, for this point. You see that this point, the height of this point is lower than the points around that point. But of course, this point is higher than that point. But still, we call it a local minimum point. Yes? So it means that when you look at the point locally, this point have a lower height with respect to the points in close vicinity. And this is a local maximum. So for example, this is a local maximum in my graph. This is a local minimum. That one is also a local maximum. But if the graph goes continue forever, this is not only a local maximum, but it is also an absolute maximum. Yes? Because it is not only higher than the points in the vicinity, this is the highest point of the graph. So that's called an absolute maximum, okay? And these 2 points are called terrace points, okay? So I want to understand, so the point is that if the function is given to you, it means that I have the rule of my function, whatever that is, not the graph. How can I determine the coordinates of these points? Okay, so that is the question. I give you the rule of my function, and I ask you for that function, locate and determine all local maximum and minimum points, and also terrace points, if there is any of them. So how can I determine that? Do you remember? Of course, I want you to remember and understand. I want you to visualize this. So how can I find these points? First, let us see what is common with all those points. What is common? Yes? Yes? Yeah, just say it.
The line of tendencies.
Yes, if I draw a tangent line here, if I draw a tangent line here, if I draw a tangent line here, if I draw a tangent line here and here, all of them are horizontal tangent lines. And if it is a horizontal tangent line, what does it mean? It means that the derivative at that point should be 0. So for example, if this point is A, if this is B, if this is C, and if this is D, this is E. So if I ask you what is f prime at A, the answer is 0. If I ask you what is f prime at B, the answer is 0. What is f prime at C? The answer is 0. F prime at D, the answer is 0. And finally, f prime at E, the answer is 0. So you see that this is a common feature of local extreme points and also at the terrace points. Okay, so this is the commonality. So we already have some clue what to do. So it is a good idea to determine where the derivative is zero. If my goal is to locate the extreme points, a good idea might be to find where the derivative is zero. Yes? But there are two problems in front of me. Yes? What are those problems? So my question is that I give you a function. I want you to find these points. What you do, you take the derivative of the function, and then you put the derivative equal to zero, and then you solve it and find the x values. If this is the graph, what do I get when I solve this? What do I get? I get A, B, C, D, and E. Yes? I get A, B, C, D, and E. But this is already a good progress, because if you don't know anything about the function, how many potential points are there for local extreme points and terrace points? If I give you a random function and you don't know anything about your function, how many potential points might be there for this? There are infinitely many, yes? But I have narrowed that down to this very small list. Instead of having infinitely many points in front of me, by taking the derivative and put it equal to zero, I get just a finite bunch of them. Yes? So this is already a good progress. But the problem is not solved yet, because as you see in this picture, for example, in this case, C and E are fake ones. They are not maximum or minimum. They are actually terrace points. So, but because I do not have access to the graph yet, I need to find a systematic way to be able to recognize which one is the real one and which one is the fake one. By fake one here, I mean the terrace one. This is one problem. What is the second problem? Yes?
If it's a maximum.
Yeah, which one is maximum, which one is minimum? Yes, because when you put the derivative equal to zero, you get a bunch of numbers. Even if you know that they are real, you still don't know which one is a maximum, which one is a minimum. So the second question is that how can I recognize this? So the first part was simple. So all these points that you see have one property in common. The tangent line is horizontal there. Now that I know that this is my list, I want now to see the differences, because I want to differentiate them from one another. So I don't look for similarities, I look for differences. So what is the differences between these points? Just by visualizing. I don't want you to remember something. Of course, you can also remember. But what do you think? What is the difference between a local maximum and a local minimum? Of course, there are differences. We can immediately detect them. But I mean a difference so that you can formulate it analytically and use the notion of derivative to recognize them, one from the other one. Yes?
Well, the slope before and after.
Yes. So for a maximum point, before that point, the function is going up. When it reaches here, it becomes zero, horizontal, and then immediately it goes down. So for a local maximum, the left side, the function is going up. The right side, the function is going down. But for a minimum, what happens? For a minimum, the left side, the function goes down, and then the right side, the function goes up. So going up and down is similar, but in which way they go up and down is different. For a maximum, the left goes up, the right goes down. For a minimum, the left goes down, the right goes up. And for a terrace point, what happens? Either both of them are going up, in this scenario, up and up again. In this scenario, down and down again. Okay? So it means that it is a good idea to understand this behavior analytically. Now, how can I formalize this? Okay, so here the function goes up. How can I use the idea of derivative to understand the behavior of going up? You remember? You don't need to remember, just look at the picture geometrically. So you see this part of the graph is the going up part. By the way, what is the terminology? Do you remember? When I say the function is going up, there is a word for it. The function is? No. No. The function is? Increasing. Increasing and decreasing are the words. Yes? So this function is increasing here. But let us detect what is the main feature of the increasing part of the graph. For example, let us look at here and then draw a tangent line here. And then let us look here and draw another tangent line there. I don't know, let us look here, draw a tangent line. The tangent lines are not visible. Let me make them with a different color. So this is the tangent line. This is the tangent line. This is the tangent line. Of course, these tangent lines are all different in general, but they have one thing again in common. What is that one thing? If it is the increasing part, they have one thing in common, yes? Why? Because you see that all of them have this type of lines, yes? These type of lines have positive slope. Is that right? They have different slopes. You see the function is actually here, the slope is becoming smaller and smaller. Okay? But still all of them are positive. So if the slope is positive, it means the derivative is positive. So we see that on the right side, where the derivative is positive, the function is increasing, or the other way around. If the function is increasing, the derivative is positive. So we can use the sign of the derivative. By sign, I mean as this one, yes? But I can use the sign of the derivative, positiveness or negativeness of the derivative, to understand the increasing or decreasing behavior of my function. Yes? We realize that on the increasing part, the derivative is positive. What happens on the decreasing part? For example, let us consider this decreasing part. Okay? If I start drawing tangent lines here, what happens? Here, I have this tangent line. Here, I have this tangent line. I don't know, here, I have this tangent line. They are different tangent lines, but again, what is in common in all of them? All of them are of this type, yes? So they have negative slope. So this means that on the decreasing part, the derivative is negative. Is that understandable? Yes? So we realize that the derivative on the increasing part, the derivative is positive, or if the derivative is positive, I know that my function is increasing. And if the derivative is negative, my function is decreasing, or on the decreasing part, the derivative is negative. Yes, is that clear? Okay, now we can understand that. So what I want to write is now the algorithm of the first derivative test. Okay, so we had this before, the first derivative test. Test for what? Test for local extreme points. So if I want to locate, now I want you to tell me algorithmically. I give you a function with a rule, you don't have access to the graph, and I want you to follow steps like an algorithm, so that at the end of that algorithm, you have the extreme points of your function. And of course, terrace points, if any. So what is the first step we do? Yes? Yeah? Take the derivative. Yes? Number two, what do? I need to find my candidates. My candidates are among those points for which the derivative is 0. So it is a good idea if I put the derivative equal to, so let me write solve f prime of x equals to 0. And let us say that we solve this and we find x equals to a. Of course, I get a bunch of numbers. Don't get confused. I'm just, if you want, I can write it as x naught, okay? here. You solve it, either you get no solutions or one solution or a bunch of numbers. I am taking x naught as a representative. Okay, and now the next part, I need to realize if this is really a local extreme point, and if it is it maximum or minimum? For that one, I have to, if you remember, to set up the sign table. Set up the what is so-called the sign table. Yes, different books have different way of drawing them. I will follow what is more common. It's not exactly the one in the book, but one thing is in common that all of them have 3 rows. The first row is for x by convention. The second row is for the derivative, and the third row is for the function itself. And what you do, you put these numbers here on the first row in the ascending order from left to right. So here, let us imagine just we have 1 point, so I put x naught here. Okay? Immediately below x naught is the derivative row. Okay? So what do you think this will happen here? What does it mean? It means that if you go to your derivative and replace x in your derivative with x naught, what will happen? What should I write here? What?
F of x naught.
No, f of x naught is the third row.
F prime of x naught, sorry.
Okay, but yes, you are right. F prime of x naught is more than that. What can I write instead of f prime of x naught? 0. Why? Because I myself put it equal to 0 and solve that. When I solve that, I got x naught. It means that if I put x naught back in my derivative, the answer is becomes 0. Of course, what you said is correct, but I can write it simpler. Here is 0. Yes? But then if I want to write something here below this one, this is the f row. So I have to put information in f. If I put my information in my function f, because my function is not clear yet, what I can write at most is f of x naught. Yes? Okay, and then I try to determine the sign, positiveness or negativeness of f prime, when x is less than x naught, and also when x is greater than x naught. Okay, let us assume that how many possibilities can happen? I have 2 signs, plus and minus. So I might have these scenarios, plus minus, minus plus, plus plus, and minus minus. These are 4 possibilities. Yes? So what happens if I have plus minus? If I have plus minus, it means that the derivative is positive on the left-hand side of x naught. If that is positive there, according to what we understood, it means that the function is increasing. This is the symbol we use for increasing function. And then immediately after that, the derivative is negative. It is going down. If this happens, this is 100%, we are 100% sure that this point x naught and f of x naught is what? A local maximum point. Okay? And it might happen, so this we understood. Then I have the scenario of minus plus. So let us, I'm a little bit lazy, but let me just draw it. X naught, again, let me just do it quickly. I don't need explanations here. But then this becomes minus, this becomes plus. Of course, in this case, this goes down, this goes up. This means that x naught and f of x naught is what? A local minimum point. Let me also emphasize here the word point. When we say point, it means that I should have x coordinate and y coordinate together. But there are 2 other possibilities, so this is also checked. Now, there are 2 more left. So let me just draw them quickly. So here I have x, f prime f. Here I have x naught, 0, f of x naught. Let me just draw one more. Okay, so it might happen this is positive, positive, so it means that it goes up. Or it might be negative, negative, it goes down, it goes down. But in both cases, I have a terrace point. So this, or this means that x naught and f of x naught is a terrace point. By the way, if someone asks you what is a terrace point, what a terrace point is, you would say that the terrace point is a point on the graph so that the tangent line is horizontal, but it is neither a maximum nor a minimum. Okay. So this is the content of course I had to write a lot, but this is extremely simple. This is called the first derivative test to determine the extreme points, local extreme points of a function. Let me emphasize, sometimes I forget to say local, but it is important to say local. This is not part of your lesson, but let me just for your information tell you that this algorithm cannot detect all possible extreme points. Can you imagine one? I mean, if you go to university, you have to add one more line to this algorithm if you want to be on the safe side. Yes?
It must be a continuous function.
Yes, but let us assume that this function is continuous. Still, this is not enough. Yes?
The function will like the what you call it, like bounce. So the where the main is not like
Infinite.
Yeah.
No, that's this is still work if that is in the middle.
Yeah, and it's
Yes, but let us assume that we have an unbounded function. There is also one scenario that this does not work. Not doesn't work. You have to add one more step to it so it works. But you can imagine that. What type of, can you give me an example of a local extreme point? Local maximum point that this algorithm in this form is not able to is not capable of detecting that. Yes?
When the extreme point is on the x-axis.
No, it will get that. For example, if you have this scenario, if I don't know if I understand you correctly, this is still working for even this case. It doesn't have any problems. What is the problem? No, imagine there are some extreme points that I'm not discussing with you here. Yes?
Is the extreme point is at the end of the line?
There is no end. Where is the end of the line? Yes? And yeah. Yes?
When k is 0.
No, K0 is detectable. All the cases that the K is detectable. No, be careful, it's not hard. So is this algorithm, let me just draw it for you. Is this algorithm is capable of drawing this one? Okay, so is this point a local extreme point or not? Is it a local maximum point or not? Yes, because it is higher than the vicinity of the point. But this algorithm is not capable of detecting that point. Okay, why? Because this algorithm is only capable of detecting local extreme points at which the tangent line is horizontal. But there is no tangent line here. Why? Because that's a sharp point. At the sharp point, the function is not even differentiable. So the derivative at this point does not exist. Okay? Because the derivative exists if I have a tangent line, but I hope that you understand intuitively that there is no tangent line here. Do you think this is a tangent line here? No. If this is a tangent line, this is also a tangent line. This is also a tangent. If this is the tangent line, all of them should be a tangent line, and this is not. So be careful. This algorithm is not capable of detecting this local maximum point. Okay? So let us imagine. I want just to, this is not part of your lesson, but I want you to be imaginative. Okay, so do you think, how can I modify this algorithm? In the university, you will learn about this. It is very simple, okay? How do you think I need to modify this algorithm to be on this, to be capable of even detecting this situation? So the first step is still the same. Okay, the second thing I have written, solve this one equal to 0. There is a, let me call 2 prime. Okay, what is 2 prime? Yeah, you just saw that. Yes. So here, when I put the derivative equal to 0, I am getting some candidates at which the tangent is horizontal. But 2 prime, the next step, determine where the derivative does not exist. Okay? So this also gives you a different set of points. And then you use this third one for all of them in one place. Okay, but I don't want to confuse you, but I just want you to be able to look a little bit ahead of you. Okay? But for your lesson, this is the only scenario that we will face. Okay? By the way, let me also try to see how you think about this problem. For example, let me see if I remember. I was imagining something now. Okay, so let me just play around with this concept a little bit. I draw a graph like this, and then I will do that. By the way, this should be a continuous function. So what Sergey said is important, right? Well, because this is the only scenario that you have. I wasn't very explicitly rigorous here, but you have to have a continuous function. Okay, but the concept of the local extreme point, what do you think it will be here? So I have a graph like this, and let us say that this point is A, this one is hollow. Okay, so let me see, what can I do? Okay, so let me just do this. Okay. Let me see if I imagine this correctly. So this is the graph of my function. Of course, this algorithm, even the modified version, is not capable of doing that. Yes, because that function is not continuous. But let me say that the graph that you see here in front of your eyes is the graph of a function that I call it function f. Yes? It consists of 2 rays starting from a point going to infinity. If you want, I can also add this. And then one single point is gone there. Now my question for you is, and I will give you this point is, say, alpha. And now A and alpha belongs to the graph of the function, yes? But A, and if I want to make it more clear, if I say A and beta, which one belongs to the graph? A alpha or A beta? Yes, which one? A beta is on the graph, or A alpha is on the graph? No, but this is nothing to think. That is the convention of the hollow circle and the filled circle, filled dot and hollow dot. Which one is on the graph? Alpha. So this is on the graph, this is not on the graph. Okay, now my question is that, do you think that this point is a local maximum or a local minimum or neither? This is good. I mean, this is a good question. Think about it, okay? Is this point for this graph that I have drawn, it's a pathological graph, yes? It is actually a very strange graph, yes? But forget about this. Let us imagine. Okay. Is it a local maximum? Is it a local minimum or neither? But yes? Yes, Rasmus?
I would say that it's a local maximum
Yes.
by like definition.
Yeah, by definition. This is intuitively seems to be a minimum or something, but this is a local maximum. Why? Because when I say this is, the height of this point is this much, but the points in the vicinity are not there. The point on the vicinity on the graph are on these black lines. And in the vicinity, when I go a little bit to the right, this would be my height. If I go a little bit to the left, this will be my height. So if I stand at point A, this is my height. If I go a little bit to the right, the height goes down. If I go a little bit to the left, the height goes down. So that is, by definition, is a local maximum point. Yes, is that understandable? Yes?
Can you define local again?
So local maximum is a point whose height, okay, is higher than all the points in a very close vicinity to that point.
Well, what defines a close vicinity?
So if I
Like
want to
the
make it
previous
more,
point and the next point are like a collection of
no, if I want to, so because I understand what you mean, because the notion of close should be defined clearly. So if I want to define it clearly, so I would say a point x naught and fx naught is a local maximum if there is an interval, no matter how short the interval is, around x naught, so that for all the points within that interval, f of x naught is more than other f of x's. Yes? Is that understandable? Yeah, I don't want to spend time on these things because they are a little bit more advanced ones. So when I say this point is a local maximum, it means the height of this point is higher than the points in the vicinity of that. But if I want to make it more clear, I would say that this point is a local maximum if there is an interval around x naught, okay, so that f of x naught is more than f of all other x's within that interval, no matter how short the interval is. Yes? So might be this function goes up here, and then it goes down, and then immediately it goes up. But still, this is a local maximum, because I can make the interval extremely short then. In that very, very short interval, the height of this point is still higher than those points. In that very short interval. Okay? That is the real definition of local maximum point. But it is better to rely on your intuition rather than very precise mathematical definitions. But is that solving the problem for you? Yes? So because you hear, even here, when I say vicinity, so I don't know, if you are very generous, this is still vicinity. Yes? But no, when I say this is a local maximum, it means it is possible to find an interval, no matter how short that interval is, so that f of x naught is more than f of any other x's within that interval. Yes? If I can find one single interval like that, then it means that point is a local maximum. Yes? Okay, so anyway, I just wanted to, because these concepts, if you play with them in your brain, they will implement it in your brain. Otherwise, you will forget them soon. So this is why I think this is a good thought exercise that we go through it. Okay, anyway, you understand the algorithm. Now let us do some examples. Let me see if I have some examples here. Okay, let me start with a simple example. The function is, so the question is this. It's a very standard question. Determine the extreme points. When I say extreme, I mean both minimum and maximum. Determine the extreme points, if any, of the function f. Okay, number one, So let me give you this function. 10x to the power of 3 minus 3x to the power 5. This is actually a Math 3C problem. In Math 4, we can ask you the same question. Usually in the national exam, they don't ask you about this because this is exactly Math 3C question. They might give you a function in which you have some kind of function that you learned how to differentiate for in this course. Okay, for example, the product rule, I don't know, the chain rule or something like that. But let us start with this example. By the way, this is not the simplest possible Math 3 example, but let us start from this one. Okay, I want to follow the algorithm step by step, and I put the number here. Of course, it is not important to itemize them, but I want to just do that for you see that I am following the same algorithm. The first step is to, oh, okay, sorry, I have to continue the question. The function and specify the nature of them. Okay, so the first step is to take the derivative, which is 30x squared minus 15x to the power of 4. Okay, the second step, to put it equal to 0 and solve it. Okay, in order to solve this, because this is a 4th degree polynomial equation, I have to factorize it, but the factorization is extremely simple here. I factor what? 15x squared, and then from here I get 2, and from there I get what? X squared. Yes, agree? And then equate it to 0. But this is the product of two numbers is supposed to be 0. It means that either the first one is 0 or the second one is 0. But this means that x is 0. There are two answers here. What are they? Plus or minus the square root of 2. So it means that I have only 3 candidates for extreme points. But first of all, I don't know if there is any fake one there. It means that if one of them or both of them, I don't know. Is there any terrace point there? And if one of them is an extreme point, what type of extreme point is it? Is it a maximum or a minimum? Okay, so this means that I need to go to the third step. In the third step, I set up one table. Of course, you in principle can set up 3 tables, but it is not needed. You just set up one single table for all of them. But the standard one is that the first row is x, the second row is for f prime, the third row is for f. And then you have to put these numbers in ascending order from left to right. I have 3 numbers, minus the square root of 2, 0, and a square root of 2. So I put them in order. Yes? In your lesson, usually these are always 0. Yes? Because I myself put the derivative equal to 0 and found these numbers. It means that if I put these numbers in the derivative, it is natural to get 0 back. Yes? And then I want to fill up the f row. So be careful, don't get confused. For f row, you have to refer to your original function and put these numbers inside the function. It's a little bit annoying, but let us just do that. So let us put the square root of 2 first. If I put the square root, I can go to scratch paper. Of course, you can use the calculator and whatever, but let us just do it here. Square root of 3 to power 3 means the square root of 2 times the square root of 2, which is 2, and then another square root of 3. That 2 becomes 20, square root of 2. Okay, that one is annoying. So this one becomes what? X to the power of 5 is x to power 2 to power 2 times x. So this one is 2, 4 square root of 2, yes? And then minus 3, it's minus 12 square root of 2, so it's 8 square root of 2. Are you with me or I am lost? Do you agree with me? So let me double check. The first one is correct. The second one gives me 2 factors of 2, 12, 1 factor of 2. Yes, that's correct. So here it becomes 8 square root of 2. Yes? What do you think this one will be immediately? We are lucky here because this is an odd. This is also odd. So if I change x to minus x, the function will pick up an overall minus sign. Yes? So this becomes definitely minus 8 square root of 2. If you don't believe, you can just calculate. And what happens if I put 0 in my function? Okay, this is easy. It becomes 0. Yes? Okay, the second, now my task is actually to determine the signs of the derivative here. I will tell you one thing, if you're happy, okay, we continue, but if you're not happy, you can ask me why, of course. But let me tell you what to do first. So I pick a random number before minus the square root of 2 on the left-hand side of minus the square root of 2. Choose the simplest and wisest possible one. Okay, what is the choice? Minus the square root of 2, this, I would choose minus 2. Yes? Because I want to be less than minus the square root of 2, and probably the best option is minus the square root of 2. And then, minus, don't write that here. So you just take minus 2, and you put it back into your derivative. Okay? Of course, you can put it here. But because I have the factorized version of my derivative here, it is much easier to work here. And on the other hand, because this one is always non-negative, so it doesn't matter, because what matters to me is the sign, positiveness or negativeness of my derivative. This is my derivative. This part of my derivative is always non-negative. So this is the only important factor for me. And if I put minus 2 here, it becomes positive 4. 2 minus positive 4 is negative 2. And this one is always positive. So when I multiply them, definitely it becomes what? Yes? But it's a claim there, because I just checked it for minus 2. Minus 2 is one single number, but I am claiming, don't worry, it will be minus 1 at every number less than minus 2. If you want, I can explain that, but let us take it for granted for the time being. Understandable here? I go to the next step. Between minus the square root of 2 and 0, I pick also a number. What is that? Minus 1 is the best option. And I put minus 1 back again into the derivative. I don't need to be worried about that because this is always positive. I put it here, it becomes 1. Positive times 1 is positive. And then I go between 0 and the square root of 2. I pick the best choice. Here is 1. I put 1 again in my derivative. This is positive, this is positive, it becomes positive. Yes? And then I go on the right-hand side of square root of 2. For example, I choose which number? 2. I go back to my derivative, I put 2 there. This is positive, this is negative. Multiplying is negative. Yes? Yes, okay. And now what does it mean? It means here the derivative is negative, so the function is decreasing. Here and there, on both of them, the function is increasing because in both of them the derivative is positive. And then in the last one, the derivative is negative, so the function is decreasing again. Okay, now what happens? This point you see, this behavior is for minimum. This behavior is for maximum, but this behavior is for the terrace point. So I have so minus 2 and minus 8 square root of 2, the local minimum. Square root of 2 and 8 square root of 2, the local maximum. And then 0 and 0, which is the origin, you see this point and that point, is the terrace point. Yes? Understandable? So this is the essence of the first derivative test. Yes?
Why is the third row needed? Is it needed to answer this kind of question?
Yes, yes. The third row, yes, I will tell you because I need these numbers as well.
And why is that?
No, because they are talking about the point. This is also a good question. So let me remind you, when they say point, you have to be careful. You have to give the x and y coordinates together.
The extreme
Point.
determine the point.
Yes, but let me write it down here for you. So when we say let me call it for minimum. So the local minimum point. Here you have to say minus square root of 2 minus 8 square root of 2. They might ask you where the local minimum is attained, or I don't know, occurs, or assumed, or I don't know. Something like this is attained. You have to answer x equals to minus a square root of 2. And then sometimes ask you, what is the minimum, the local minimum? Yes? And sometimes they emphasize and put value also. Either they can ask you, what is the local minimum? Or they can ask you, what is the local minimum value? Okay? Then you answer what? Minus 8 square root of 2. Yes.
Since we're determining extreme point, shouldn't the terrace point be excluded?
Yes, you can exclude that. Yes, you are right. But let us take it for completeness.
Or do you want to?
We can add something there, yes. So we can say determine the extreme points or terrace points, if any. Yes, this is better. Yeah, I forgot to write, but you're right. So you see, this is good. We were able to detect the terrace points and local extreme points with this algorithm. So as far as my function is continuous and as far as my function is well behaved, when we say well behaved in mathematics, it means continuous and differentiable. Continuous means that I can draw it one pen stroke, and when I say it's differentiable, it means that I do not have sharp points. Okay? So this algorithm, as soon as you have a well-behaved function, works fine. And it is capable of answering all of them. By the way, we can also sketch the graph. Before going to the next example, let us try to review the sketch of the graph. This is also part of this course. So if I want to sketch the graph, of course the numbers are not so friendly, but let us try to do that. Okay, so I don't need that much on the x side. I need this on the y side. Okay, so I need to highlight these important points, local extreme points and the terrace point on my graph. And I have the coordinates in front of me. So minus square root of 2. So let us say that this is minus square root of 2. I might exaggerate a little bit. And then minus 8 square root of 2. Let us say this is minus 8 square root of 2. So this is my, so I don't need to exaggerate that much because there is not enough space to draw the graph anymore. Okay, so here, let us say this is minus 8 square root of 2. So that point is my local minimum. this is important. When I say it's local minimum, it means that the graph around this point looks like this. When I say looks like this, it means that this is the generic behavior. It might be very narrow, it might be wide, or it might be moderate, I don't know. But this is the type of shape that you expect around the local minimum point. And then you have a terrace point, which is 0, 0. So this is your terrace point of which type? Because terrace points are of this type or of this type. Which one is this here? Because in both directions it is going upward, so it should be of this type. So it means that around this point you have something, you have a behavior like this. How steep is that? I don't know. But qualitatively, this is what you expect here. And then you also have this local maximum point. So the local maximum point is the square root of 2, and then 8 square root of 2, let us say it is here. And then that is a local maximum point, so it means that around this point, the graph should look like that. Okay, before going to the here, what do you think will be the behavior of my function here? So, of course, it will increase, but do you think it will always increase, or this is the danger that at some point it goes back down? Yes? Do you think that will happen here? So this will go up, but do you think it will go up forever, or at some point it returns back? Yes?
It'll always go up because they're on the extreme point.
Yes, because if this is supposed to return down again, then it has to have another local maximum point. But there are only one local maximum point. So this is important, by the way. Be careful. You might underestimate this. You put this in GeoGebra, it gives you the best possible picture. But the algorithm there is more or less giving you using these ideas. Because by looking at one part of the display, there is no guarantee there are no surprises if you go beyond the display. Yes? But this method tells you, no, there are no surprises. Don't worry. This will go forever. This will go up forever. Okay? And what about the same scenario? This tells you that this will go down forever. Because there is no going up again. Going up means another local minimum point, which we don't have. And then, of course, here we will have this scenario. Something like this. It is a very awful picture, but it captured the essence of this graph. So this gymnastics you expect, okay? So if you didn't catch this point, might be you connect this directly to that. Then you miss this behavior there. The whole point is to not miss these qualitative behaviors. Yes, please.
You said for maximum and minimum points, the more exact definition is you can find an interval where that point is the largest or smallest point. In
Yeah.
the interval. Is there a similar definition for a terrace point? Like, is there a more exact way to?
That's the same thing. You can find an interval around that point, so that terrace point is higher than the points on the left and lower than the points on the right, or the other way.
But I mean, isn't that true for every point? But if the
No, because the derivative should be 0.
yeah, yes.
Yes, you are right. If I exclude that, of course, I will lose. Yes. Questions?
Yes. So then there's
Terrace points cannot be.
point cannot see terrace points.
Which points?
Point that's with graph is sharp.
No. Included in because terrace points are special cases of inflection points. Yes, an inflection point, the second derivative should also exist. Yes, you are right. We don't have that behavior. Because otherwise, if I exclude that, this can also be, do you remember something about inflection in Math 3C? So if I ask you what is the inflection here, it is concave down, and this one is concave up. So the inflection point is a point that the concavity is changing. The concavity is really changing here, but it is not an inflection point in the usual sense of an inflection point. So in the definition of the inflection point is that the derivative should exist, the second derivative should also exist. So yes, sharp points are not categorized here.
So the-
But yes,
it needs to be differentiable for you to talk about.
yes. Okay, but maximum point might be this is the maximum point. So even though this is not differentiable, but it is sensible to talk about local maximum points. But it is not sensible to talk about the terrace law. Okay, one question is that why do you think this method works for determining the sign? Because let me ask you the question. What is the question? If you remember, for example, if I wanted to determine the sign, how many points are there between 0 and square root of 2? Infinitely many points. I just picked one random one, which was the simplest one, 1, and I checked the sign of derivative for that single number 1, but I claimed more. I claimed that it is always possible, even though I checked it only for 1. So in principle, if you want to be rigorous, you have to say why this method works. But why do you think there is one behavior that guarantees this? I want you to tell me the name of the behavior. There is one name, one word, which is representing the behavior of something, in this case the derivative, that guarantees this method is valid. What that behavior is? Yes?
Continuity.
Exactly. The derivative is continuous. Okay? Because what is the derivative? The derivative is again another polynomial, so it is continuous. Why is that? Because if you have a continuous function, let us say that I have a continuous function, so let me call the derivative here p. Px is my derivative. Okay? If I want to draw the graph of this function has some zeros. What are the zeros of this function? I found that. Minus the square root of 2, 0, and a square root of 2. So it means that if I am able to draw the graph of this function, what happens? It will hit the x-axis at 3 points. Yes? Okay? So the graph should pass through these 3 points. Now, I picked a random number, say here. What was my number I picked here? 1. I checked that it is positive for 1. What does it mean? It means that if I pick number 1 here, what was the number? Do you remember if I put 1 here, 15, and this is 1, so it is 15. Okay? So I randomly picked one number in this interval, which was 1, and I checked that p of 1 is 15, and it is positive. And then I said, okay, it will be positive for all of them. Is it clear? Because you see, this is the function should pass through this point, should also pass through this point, but by this random check, I realized that the function should also pass through that point. And my function is continuous. So I don't know how it goes, but it goes continuously, up and down. Yes? Is it possible that I have any, and you see that because of that one which was positive, all the graph will be up. So every number will be positive again. So do you understand? This continuity guarantees that from here, I have to go here, I have to go there, but continuously. Okay? So if one of them is up, all the curve should be above the x-axis, not just one single point. There is no point. Do you agree with me or not? Yes or no? Is that clear? Okay, so we are on the safe side. But this argument works if my derivative is continuous. And then the examples that you have or all of these type of examples. But I want you to know that your methodology collapses if I do not have the continuous derivative. Yes.
But can derivative not be continuous?
Of course. The famous example is this example. This function x not equal to 0. X squared times sine of 1 over x if x is not 0, 0 if x is 0. Okay? This function is continuous, differentiable, but its derivative becomes discontinuous. Yes? So we have those kinds of functions. Okay? This is the classic example. Yeah, intuitively it is not that clear to imagine, but this is a function which is continuous, differentiable, but if you differentiate it, the derivative becomes discontinuous at the origin. So we can have the function like that. Okay, but are you happy with this method? So as far as the derivative, so for example, here, why it is always negative? I chose a random number, it was -2 there. So -2 is somewhere here. And I check that it becomes a negative value. Okay? But you know what is going to happen. So by the way, this function goes down and it has to go up again because that is the 0 of my function. Then it means that it is always negative. Yes? And by the way, you really don't need to do this. By the way, now can you give me a better trick now? I just realized. So we don't need to check random numbers one after the other, do we? Yes, I think so. Because you see, my function should pass through this point and through this point, and then it is already giving me the behavior of decreasing. Yes. So why that is not working here? Oh.
It should work.
No, it is not working, you know, because when we checked a random number between 0 and 1, what happened? Between 0 and 1, between 0 and a square root of 2, it was that one. And then between these, I chose which number, do you remember? -1. And when I put -1 here, it again becomes positive value. So you see, so how is that possible? Yes, it comes here, but it goes up and down again. Something like this. And then I chose a number here, it becomes negative, so it goes there. Yes? The important thing is that that one random point that I picked guarantees the positiveness everywhere on that interval. And then this random number that I picked, and it was negative, guarantees the negativeness of all of those numbers. So I just want you to know that the derivative being continuous is crucial here for this for this method to work. Okay, any questions? Yes.
So on the graph of the derivative, a local minimum goes from negative to positive. A Cherys point goes from just touches the graph, and then from either positive to positive or negative to
Yes, if you yes, we can systematize this a little bit. So, for example, if someone gives you the graph of the derivative, for example, I don't know, something like this. Okay, so for example, let me say this is A, this is B, this touching point is C, this is D, this is E. But this is not the graph of my function, this is the graph of the derivative of my function. Okay? And now I want to understand the nature of these points for the original graph F that I don't have access to. Okay? So that is more or less your question. Okay, let us try to solve that problem. This point is the x-coordinate of a point on the graph. Okay, so this is, I'm asking you a point A, and I don't know what is F, but let me just write A and F of A. Now my question for you is that, do you think that this point for the original graph that I don't have access to is a maximum or a minimum or a Cherys point? or neither of them?
Maximum.
You say it is maximum. So why is that? Because before this point, this is the graph. Is the graph, is the derivative positive or negative on the left side?
Is this a graph?
This is the derivative.
Okay, this is positive.
It's positive. Why? Because the graph lies above the x-axis, and this is the derivative. So by looking at this, I see that on the left side, this is above the x-axis. So this point, the derivative on the left is positive, so it goes up. And then immediately after that, the curve goes below the x-axis, so it means the derivative is negative. Yes? So this point is local max. Be careful. You might say this is not a local max. Yes, this is not the local max of this curve, but this curve is f prime. I am talking about the original f that I don't have access to. Okay? So I am saying that fa and f of a is the local maximum of the original graph. Yes? Understandable or not? Happy or not? So if you understand, you need to tell me what this one is. For this one, this graph is not, this point is nothing. It is just a zero. Okay? But for the original graph, this point is, yes? Local minimum. Because on the left side, the curve is below the x-axis, so it is negative. On the right side, the curve is above the x-axis, so it is positive. So negative, then positive. So it is a local minimum. Let us look here at point C and f of C. What that type of point is, what is the type of this point for the original graph? What is this point for this graph? What is this point for the same graph that you see?
A local minimum.
A local minimum. But for this graph is a local minimum. But for the original graph is
Terrace point.
a terrace point. Yes? Because before that, the function is above the x-axis, so it is positive. And after that, the function is above the x-axis, positive. So, but you tell me, what type of terrace point? Because we have two types of terrace points. Which one is this one?
Going upward.
Yes, because on both sides it is positive. So this is a terrace point. Yeah, it is a good question. So let me write terrace point of this type. Okay, another important point is what? D, but you can also immediately tell me, hopefully, what is D. D and f of D, what is that? Before that, the graph is positive, so the function is in the original function is increasing. And after that, the original function is decreasing. So this is a local max. And finally, what about E?
Terrace point.
It's a terrace point. Which type?
Going down.
Going down. Of this type. Yes? So that is also possible, yeah? But let me ask you one question. Now, of course, we haven't done that, but can you tell me what is this point for the original graph? Yes?
It's when it touches the x-axis, I guess.
No. You cannot know about the height. There is not one function, by the way. There are infinitely many functions whose derivative is this. If you have one function, you can add any arbitrary constant to that function. The derivative will be the same. Yes? It will be inflection point. Because when I say here, it means the derivative of this function is 0. But this function is already f prime. So its derivative becomes f double prime. F double prime is equal to 0 is related to what we will learn later, inflection point, if you have forgot. Yes? Okay, I want to give you one more example of Math 4 because we didn't have this in Math 3C. But do you have any questions here? Okay? Okay. The Math 4 question, let me choose it from the book. Okay? It's an E-level question in the book. We will solve a little bit harder ones later, but let us try to do one more example at least, because this is mainly what I told you in Math 3C. So number 2, f of x equals to x squared e to power x. So this is the one that you couldn't solve in Math 3C, not because it is complicated. Why?
We didn't have the chain rule and also
The chain rule is not relevant here. Which rule is relevant?
product.
The product. Okay? So, but I will follow exactly the same algorithm. Okay, the first step is to take the derivative, but that's the product rule. The derivative of the product is what? The derivative of the first one multiplied by the second one itself, plus the first one multiplied by the derivative of the second. So I will do this here. The derivative of the first one is 2x multiplied by the second one, plus the first one itself multiplied by the derivative of the second one. But what is the derivative of the second one? The famous function is itself. This is the first step. Because of this step, I couldn't tell you this in Math 3C. That's it. But the rest, you could do it in principle. So number 2, I put the derivative equal to 0. So then what happens? It means 2x e to the x plus x squared e to the x is supposed to be 0. Okay? So how can I solve this equation? By factorization. For example, I can factor x from the left, e to the x from the right. It doesn't matter in which direction, but I prefer to write it more beautiful. Okay, so this becomes 2 plus x. So if you multiply these in, it becomes 2x e to the x. If you multiply these two in, it becomes this. And now how many numbers I have? I have 3 numbers. I know something. I know the product is 0. So this means what? It means that the first one, either the first one is 0, or the second one is 0, or the third one is 0. Okay, so this is already solved. This means that x is negative 2. But what about that one? E to the x is equal to 0. What x is?
It can't be 0.
It cannot be 0. Yes? So no solutions. Because e is 2.7 something, and if you raise it to any power, even the power negative 0, whatever, it cannot be 0.
Why is that?
What?
What is the reason?
Okay, I don't know how to say the reason at this point. So if I say 2 to the power of x is equal to 0, what x is? That's exactly the same thing.
I thought you meant that the x is 0.
No, if x is 0, e to the power becomes 1.
Yeah.
So if I say that an exponential function cannot be 0. Yes. Okay, now everything is ready. I have to set up my table. Number 3, setting up the table. It contains 3 rows. X, f prime, f. I have 2 candidates. The smaller one is -2. That one is 0. I don't need to calculate these things. I already know that they are 0. But I have to calculate these two. But I have to go to my original function. So what's the original function? This one. I put -2 there. It becomes 4e to power -2. And I put 0, sorry, this 0. I put this 0 here. It gives me 0. Okay, can I safely use that trick here? Yes. Why? Because the derivative is this function. Polynomial functions are continuous. Exponential functions are continuous. There is a theorem that the product of continuous functions is a continuous function. So I am on the safe side. By the way, for your course, you are almost always on the safe side. So I pick a random number here. Let us choose -3. I put -3, be careful. This is the f prime rule. So you have to put -3 in f prime. You could put it here, but I prefer to put it here. That's the same derivative in factorized form. And I don't need to bother about e to power x because it is always positive, so I only care about the product here. If I put -3 here, it becomes -3 times -1 becomes positive. Between -2 and 0, I pick -1. It's the best choice. Again, this is positive. I don't need to bother. If I put -1 here and here, it becomes negative when I multiply them. And then if I choose a positive number and put them there, it is clearly positive. So here the function goes up, here the function goes down, and then here the function goes up. So here I have a local maximum point and also a local minimum point. So the local maximum is equal to what? The local maximum point is equal to minus 2, 4e to the power of minus 2, and the local minimum point is 0 and 0. I want to use this opportunity to tell you to motivate you for a lesson that will come later. Yes, but let me finish this. I will answer your question. Let us assume that I want to sketch this graph. Okay. I'm just using this opportunity to motivate you for a topic that is coming later. Okay, if I want to sketch this graph, what do you do? As usual, I will highlight those important points. Minus 2 is here. Okay, so I don't know. Minus 2 is here. And this number, I don't even know what that is, but it's 4 divided by 6. So it's smaller than 1. So if this is 1, so that number is smaller than 1. So let us say that this is 4. I don't need to be very careful about these points. Okay, so that point is that point. And that point is a local maximum point. So I know that in the vicinity of that point, I have this behavior. Okay, and then I have 0, 0, which is a minimum point, and I know that in this vicinity, I have this one. Now the question is this. So on the left-hand side, on the right-hand side, what do you expect? Do you expect something like this? What do you expect on the left side? Yes? Yes. Okay, and then this one. But this is wrong. Why is that? It gives you the idea. I don't want to teach this lesson. This is the next section. But I'm just motivating you. Why do you think this is wrong? Something which is not that important, I didn't mention it for you, is really x is the domain of my function. So what is the domain of this function? It means what are the possible values that I can feed in and still the function is sensible? Every value. Everything I put here, it makes sense. So it means that the domain goes from minus infinity to infinity. Okay? But when I want to know the behavior of my function here, it means, technically speaking, I am calculating the limit of my function when x approaches to minus infinity. Okay? So you see, when I put minus 2, I get this. But how much I can go to the left? I can go up to minus infinity because there are no limitations for possible values for x. And if I want to see what happens there, it means that I have to take this limit. But I don't know intuitively, what is this limit? This becomes extremely big, but this becomes extremely small. And then there is a theorem that this will dominate that one, so it becomes 0. Okay, don't be sensitive why this is the case. If you understand it better, if you don't, leave it. But my point is that now you see that this behavior is wrong. Yes? Because by going to the left, I am not allowed to go down. So this function will actually start behaving like this. Yes? So this function is still a maximum. But it doesn't go down forever because that calculation shows that when I go to the left side, the value of the function doesn't go to the minus infinity, it approaches zero asymptotically. And that is the idea of an asymptote for a function. But what about the right side? Do you think the right side is correct? For the right side, I have to take the limit of my function, x goes to plus infinity. But plus infinity doesn't have any problems because this is plus infinity becomes plus infinity. So that behavior is correct. So that is the idea of the asymptotes that we will study later. Yes? Yes? Is the lesson finished?
Yes.
Okay, thank you.
Do you have